Good afternoon, ladies and gentlemen, dear colleagues. It's a pleasure to announce today Professor Erwin from Amsterdam for our this year first Erwin Schrödinger lecture. It's the most prestigious lecture at the Schrödinger Institute, and we are very glad to have you here. May I introduce you briefly? Professor Cox is a trained theoretical physicist, but working for a long time in the history of physics. His field of research is mainly the history of physics in the Netherlands, but he has two broad fields where he is one of the leading world experts. That's on the one side, and we here today, the physics of the history of physics of Hendrik Lorentz, and on the other side, Professor Cox is heavily involved in the Einstein paper project, now in Pasadena, California, and he spends part of his year in California to drive forward this huge project to publish all the collected papers of Einstein. And Professor Cox especially is the editor of 2 volumes, and recently, that means 2008, he published this scholarly book, The Scientific Correspondence of Lorentz, and in 2011, I think, we will see the second volume of this monument in the history of sciences. So, I think this is a very brief introduction. We are very happy to have you here. This Schrödinger lecture is organized in cooperation with the Vienna Circle Institute, and now I ask my friend Professor Stadler to say a few words. Thank you very much.
Thank you. Wolfgang. It's a pleasure to have Anne Cox here, because we met already in the 90s at the beginning of the Vienna Circle Institute. He delivered one of the first lectures, this was still in the Museumstraße, on Einstein, in connection with the Einstein project, of course. And in the meantime, we collaborated regarding the Vienna Circle Foundation in Amsterdam, and now located at the Rijksarchief North Holland. And we published some books on the Vienna Circle in the 80s with the Sultan Verlag, and also Vienna Circle collection. So it's really a pleasure to continue this exchange, and I very much hope that this good old dimension, the relation between physics and philosophy, is still informed by the lecture. I'm convinced this will be the case. Thank you very much.
Thank you very much. Thank you. I must say that I'm much honored by the invitation to give this prestigious lecture. I'm also very happy to be back in Vienna after almost 20 years, when I gave my lecture at the Vienna Circle Institute. It's always a pleasure to be in this wonderful city, and I'm enjoying myself a lot, and I hope that I will be able to contribute something to your knowledge of Lorentz and his scientific work in this lecture. So, as you will see from the title, I will talk about Lorentz's scientific correspondence in general, and then in particular about an exchange of letters he had in the spring and summer of 1926 with Erwin Schrödinger. And let me just give you a brief outline of what I'm going to do in this lecture. I will tell you a little about the Lorentz's life, some biographical information on him. Then I will give you some background on his scientific work, what his most important achievements were, in what fields he was working, etc. Then I will give you some background information on his scientific correspondence, as published in this first volume of the scientific correspondence, and there are some really interesting characteristics that emerge from this correspondence, from having those letters in one volume. Then you'll see an overview of the range of interests and the development of Lorentz's ideas on several subjects, and I will give you some background on that. Then I will switch to the correspondence with Schrödinger, and from that point on I will become a little more technical, although I hope I won't lose the more general interested people in this audience. But I will talk a little more about the specifics of the discussion that Lorentz and Schrödinger had on the foundations of quantum theory, especially on the first papers on wave mechanics and Schrödinger's first efforts to develop his famous wave mechanics. So let me just start out with a few biographical details on Lorentz. He was born in the town of Arnhem in the middle of the Netherlands in 1853. He obtained his doctorate in Leiden in 1875. Only 22 years old, and already in 1877 he became a full professor in Leiden. He was became a professor of theoretical physics. He was actually one of the first people who had a chair specifically for theoretical physics, one of the first, not just in the Netherlands, but also in the whole of Europe. He was part of the beginning of a tradition of theoretical physics that would flourish towards the end of the 19th century and into the 20th century, establishing theoretical physics, establishing itself as a separate discipline, separate from experimental physics, but of course going hand in hand with the experimentalists to have the most fruitful research in physics. Then, of course, in 1902 he was awarded the Nobel Prize. Together with his Amsterdam colleague Peter Zeeman, the experimental physicist, and this was not just for the discovery of an explanation of the Zeeman effect, but in general for Lorentz's work on electrodynamics, electromagnetism, and Zeeman's experimental work. And of course, it's always linked to the discovery of the Zeeman effect. But in fact, the Nobel Committee wanted to honor Lorentz as a theoretical physicist and wanted to honor his work in the field of electromagnetism in particular. But this being one of the first years, or actually the second year in which Nobel Prizes were awarded, they were still very strictly adhering to the statutes of the Nobel Foundation, which say that the prize has to be awarded for a discovery. And so there was a lot of problems in giving the prize to a theoretical physicist by himself. So at the last moment, they decided to include Zeeman in the prize, so that there would be a discovery, an experimental fact that the prize was given for. So Zeeman was included in the prize, but the prize was really, in the first instance, meant for Lorentz by himself. This is something that few people know, but you can actually find more details in the Nobel archives, and also there is a very interesting correspondence between Lorentz and the Swedish mathematician Mittag Leffler, who was on the Nobel Committee and who was really one of the supporters, one of the proponents of Lorentz's Nobel Prize. Then in 1912, Lorentz goes into what I call semi-retirement in Haarlem. Haarlem is a provincial town in the Netherlands, not far from Amsterdam, and he became, I say semi-retirement because he remained connected to the Leiden University as a special, extraordinary professor. He started giving his later famous Monday morning lectures. He gave them in 1 or 2 semesters a year, and he always chose the most recent and the most modern topics in the most modern developments in theoretical physics to lecture on, and they became world famous. People came from all over the country to listen to them, not just students, but also professors in Leiden or professors in other Amsterdam universities or other Dutch universities. Then in 1925, his golden doctorate, the 50th anniversary of his doctorate, was celebrated in grand style. There was many of his colleagues from abroad came to help celebrate this festive occasion. The reason why I mention this is because I have a bit of film that I will show you in a moment that actually was taken at the 50th anniversary. And then in 1928, Lorentz dies, and also his death. His death was a major event, not just in the scientific world, where of course he was mourned as a great loss to theoretical physics, But surprisingly, his death was also a major event in the Netherlands. For instance, telegraph service was suspended for 2 minutes during the funeral, which was an unheard of honor for a scientist. And if you look at, and again I have a little bit of footage about that, at the enormous crowds that were attending his funeral, just ordinary people who would come out and look at the procession come by and would go to the cemetery. It's really amazing that a mere theoretical physicist would be honored like a public figure, like a major public hero in the Netherlands. So let me start with the first. Here we go. This was taken, and maybe this doesn't work. Maybe we should dim the lights a little bit. This is total darkness. Yeah, it's still not very. Well, if you watch closely, you can see this is Lorentz. This is 1925 at his golden doctorate. Here we have it will be a little clearer in a moment. This is his funeral. This is where the coffin is being loaded on the carriage. And the reason why I'm showing you this is not so much. I thought you might be interested in Lorentz's coffin, but you might be interested in a person who will appear on the scene in just a few moments. A person that you will, I'm sure, will recognize immediately, because he's one of the icons of theoretical physics, and he was actually, here he comes. You see him? You recognize of course, the moustache and the haircut, the hairdo. Einstein was a very, very close friend of Lorentz, and he attended the funeral. But you can see that he came actually out of Lorentz's house. He was received in the house because of his close ties to Lorentz, and Einstein was much impressed by Lorentz's work and by Lorentz's personality. And he never lost an occasion to praise Lorentz, not just for his work, but also for his personality. And even as late as 1953, he wrote in a little piece about Lorentz. He wrote that Lorentz was, in fact, one of the people that had most influenced his life and had been of most influence on his scientific ideas and his scientific outlook on life. So that's quite remarkable, especially for someone like Einstein in 1953, 2 years before his death, that he would still remember Lorentz, who had died many decades before, as one of the key figures in his life and in his development. The final little movie that I'm showing you is that's the funeral, and you'll see that there are huge crowds. This is on the main square in Haarlem. Lorentz is the town where Lorentz lived. You see how many people had come out and to watch the carriages and the procession, the funeral procession. And again, it illustrates what I was saying earlier, how much of a public figure he was, and how amazing it is that a public figure would draw such crowds. I mean, I don't think how much I admire our Nobel Prize, most recent Nobel Prize winner Gerard het Hoofd, would draw such crowds at his funeral, which is hopefully still a long time in the future. So this is where it stops. So let me move on to my second topic, which is the Lorentz's scientific work. And most of you will know that his most lasting work, his most important work, was done in the field of electrodynamics. And then we're talking about, in the first place, about optics theory. That's what he started out with. His dissertation was on the refraction and reflection of light. 1875, one of the first real applications of Maxwell's theory to these phenomena, and also what he succeeded in his dissertation to actually give a satisfactory explanation or a satisfactory treatment of diffraction and reflection on the basis of Maxwell's electromagnetic theory of light. And the next step, next development in his work on electrodynamics is when Lorentz started worrying about how to make a consistent theory of electrodynamics in moving media. And then, of course, we all know that this started a development that eventually ended in 1905 with Einstein's special theory of relativity. But also, it ended also a year before, in 1904, with Lorentz's completed theory of electrodynamics in moving media, which is now known as the electron theory. A microscopic theory based on the existence of charged elementary particles, which Lorentz later first called ions and later called electrons. It's a very consistent, purely microscopic theory in which all macroscopic phenomena are derived from the microscopic basis, the microscopic atomistic nature of matter. Now, of course, we all know that one of the key elements in Lorentz's electrodynamics of moving media is the Lorentz-Fitzgerald contraction, which was introduced as a hypothesis by him in 1895, but later became an integral part of his electron theory. And in that sense, Lorentz's electron theory was a fully consistent theory, and also in 1905 Einstein came with a special theory of relativity. Electron theory was not rejected, but was seen as a viable alternative to special relativity. Those two theories were both able to explain everything that all phenomena that take place in moving media, all electromagnetic phenomena in moving media. They also both gave the same experimental predictions. So there was no crucial experiment that one could think of that would distinguish between the two theories. The only thing is that, of course, from a more philosophical point of view, Einstein's theory is, let's say, simpler because it lacks the additional hypothesis of an electromagnetic ether, which we find in Lorentz's electron theory. And if you use Occam's razor and you realize that there is no experimental way to actually to find out whether an ether exists or not, then of course it's easy to say, well, let's get rid of the ether, and then of course you automatically end up with the theory with Einstein's special theory of relativity. There are, of course, other topics that Lorentz was active in, talking about kinetic gas theory. He was a great admirer of Boltzmann's, very appropriate in this venue. He actually, after Boltzmann's death in 1906, he was invited to give one of the big memorial lectures on Boltzmann. He worked in thermodynamics, he worked in hydrodynamics, radiation theory, quantum theory, and even made some important contributions to general relativity. Now, I want to talk a little more about Lorentz's work on quantum theory, but before I do that, I will just let me first say a little more about the Correspondence edition. Fritz already showed you the volume. Volume one of two volumes, two planned volumes. The first volume publishes 433 letters in the whole period of Lorentz's active life, 1883 to 1928. A selection out of approximately 6,000 letters, and then we're talking about letters to Lorentz and from Lorentz. They were selected on the basis of general criteria, where scientific importance is the main criterion. And also, a second criterion is if we only have incoming correspondence and no outgoing correspondence, so only letters to Lorentz but nothing from him, then it's not worthwhile, or only in very rare cases those incoming letters would be published, because it's what you want to see is an exchange of ideas, an exchange of scientific ideas, a discussion, a conversation, so to speak. And if you only have one side of that, it's you lack the back and forth, which makes it so interesting. And of course, then that's of course the main task of an editor is to supply annotations, where the annotations are meant to put those letters into a proper historical and scientific context, where scientific ideas that are obsolete these days or that people wouldn't immediately understand are explained. And of course references are given if Lorentz refers to in an oblique way to a paper by, say, Max Planck. A full reference to the paper is supplied, and sometimes even a short summary of what the paper was about to give better understanding of what Lorentz was talking about. So that's the main task of an editor of such a correspondence edition, apart of course from making the selection and doing all the mundane tasks like putting things together and preparing camera-ready copy and what have you. The second volume, which I'm preparing right now, will include the correspondence with most of Lorentz's Dutch colleagues, but the core of that volume will be an exchange between Lorentz and his successor in Leiden, Paul Ehrenfest. Again, here we have an Austrian connection. Ehrenfest was one of Boltzmann's students. He was a Viennese by birth. Had his education in Vienna, and then of course he wandered out. He spent some time in Russia because his wife was Russian, and he ended up in 1912. He ended up in Leiden as a very a surprise successor to Lorentz. Nobody would have thought that he would be the candidate to succeed the great Lorentz in his famous chair of theoretical physics. Ehrenfest was a fascinating figure. Also a tormented spirit, a very good physicist, but especially one who was very good at thinking things through to the foundations of his field, and starting and opening and continuing the debate on crucial points in all kinds of fundamental developments for instance, on quantum theory. Of course, his tragic death by suicide in 1933 shocked the whole physical world, especially again Einstein, because Lorentz and Ehrenfest and Einstein were very, very close friends. Of course, they were of the same generation. So between Einstein and Ehrenfest, it was a different relationship than between Einstein and Lorentz. But there's a sort of an interesting triangle that you can see: Lorentz, Ehrenfest, and Einstein, because they were all, very much in awe of each other. They were admiring each other. They were collaborating. The days when Einstein was visiting Leiden and was having discussions with Lorentz on the one hand and Ehrenfest on the other hand, or maybe between the three of them, were for Einstein were the best days of his life and the most important meetings that he had. And it was not for nothing that Einstein in 1921 accepted a visiting professorship in Leiden. It was because that way he could be close to Ehrenfest, his big buddy Ehrenfest, but also he could be close to the great admired Lorentz. Anyway, the correspondence between Lorentz and Ehrenfest is a very interesting correspondence because it's a correspondence between two generations, but also between two totally different characters. Lorentz was a old-fashioned professor who was always a bit aloof, had a bit of distance, was never very close to his students, whereas Ehrenfest was sometimes even closer to his students than his students liked. I mean, he sometimes interfered with their personal lives more than the students would have desired. And one of the themes in this correspondence is not only the generational gap, so to speak, and the different outlook on physics that these two people had because of their different background and their being of a different generation, but also because of the inequality between Lorentz as the great master, Ehrenfest as his successor, and the burden Ehrenfest felt to live up to the expectations that people had, of him being in Lorentz's footsteps or on Lorentz's chair. And Ehrenfest never felt that he actually could live up to that he actually could fulfill expectations and could be a worthy successor to Lorentz. And that we find that theme time and again in the correspondence, where Ehrenfest asks Lorentz to even, he used that word, forgive him for being inadequate. And Lorentz trying to reassure Ehrenfest and telling him that, of course, he is a different person and he does things differently, but not necessarily worse than Lorentz himself did. And it gets very emotional, it gets very personal, and it's maybe not part of a scientific correspondence, although they discuss many scientific things as well. But it gives you a beautiful view of two different personalities, of two totally different people who were trying to work in the same field and trying to work out the same problems. So that volume will probably not appear this year, but hopefully in 2012. If one looks at the correspondence, now I go back to the first volume, then we see that this correspondence actually reflects what I was saying earlier, that Lorentz worked in many, many fields. And we see in the correspondence also this wide range of topics. I mean, it ranges from crystal physics to general relativity, and in between we talk about magneto-optics, radiation theory, kinetic gas theory, quantum theory, electrodynamics, and what have you. And the interesting thing is that Lorentz shows a sort of a mastery of all those fields. I mean, there's no field where he says, I really feel out of my depth here. I can't discuss that because I don't know what I'm talking about. And he would actually one of the things that he was doing, and I don't think he was doing it on purpose, but he was doing it because it occurred to him. He points out errors in the work of other people. Again, there is a famous example of what we find in the correspondence between Lorentz and Boltzmann in this volume, where at some point he has been corresponding with Boltzmann and actually pointing out an error in Boltzmann's work on his kinetic gas theory of polyatomic molecules. And then a few years later, he writes again to Boltzmann, and Boltzmann replies in a letter where he says, already from the handwriting on the envelope, I could see that it was a letter from you. And although a letter from you always means that I've made a mistake, I was still very much pleased to get that letter. And that's, Boltzmann, his personal touch. And there are many more people who are being corrected by Lorentz in their published work. And the other side of that coin is that he's seldom making mistakes himself. Although he does from time to time, there are a few situations where he makes an error, and then of course he blames himself. He gets very embarrassed about that. He's not used to being corrected. And there's a famous situation in 1908 where he gives a lecture on the radiation theory, and he really, he makes a mistake. I mean, he really takes the wrong turn, so to speak. And Wilhelm Wien points that out to him, and then he really has to say, well, yeah, you're absolutely right. How could I have made that mistake? That's embarrassing. That's really embarrassing, and he can't stop talking about how embarrassing it is. But that's only a few times when that occurs. Another thing is that came as a surprise, that already in the 1880s he is recognized as one of the foremost authorities in theoretical physics in Europe, which at that time meant in the whole world. I had not expected that he would at that time would be recognized as an authority, because the standard Lorentz story is that he was. And of course, to a certain extent, that's true. He never traveled. He never traveled until the late 1890s, when he finally, in 1898, was invited by Boltzmann again, and by some other people, but especially by Boltzmann, to attend one of those famous Naturforscherversammlungen. This one was in Düsseldorf, and that is his first trip to an international meeting outside of the Netherlands. And and after that, you see that he starts traveling. He discovers how nice it is to go outside of the Netherlands to meet his international colleagues and to travel. And then you see him go to meetings almost every year. Goes to an international meeting. But before that, And the idea, what people always said, was that at that point his international fame started. But if you look at the correspondence, you see that already in the 1880s, people write to him as if he was, the foremost, the most, the best authority in the field, that people that you would turn to if you had problems, that you would discuss your problems with. So it's interesting that even when he wasn't, people didn't know him in person, they knew his reputation so well that they accepted him as the authority. One of the other things that we see in the correspondence, and again that's one of the things that is illustrated quite nicely in this whole thing between electron theory on the one hand and special relativity on the other hand. I just told you that they were, in a sense, they were equivalent in their experimental predictions. That he is able to appreciate points of view or approaches of others while holding on to his own views. And in this case, he was, a great admirer of Einstein's, and he was a great admirer of the special theory of relativity. Actually, he lectured on special theory of relativity. He was even published in his published lecture notes. So he had deep appreciation for what Einstein had done. But on the other hand, he felt that his theory of electrons was to be preferred, or at least he preferred his own theory of electrons over the special theory of relativity. And one of his arguments was that he felt that maybe the ether, the electromagnetic ether, could not be shown to exist experimentally. But on the other hand, as he said, how could I visualize electromagnetic waves traveling in vacuum? Or how could I visualize electromagnetic field energy just sitting in vacuum? And one needs, as he said, you need a clothing bag to hang those things on. You need something that they would reside in. And one might as well call that thing the ether, even though it doesn't have any mechanical properties and cannot be shown, its existence cannot be shown experimentally. So here we see this nicely illustrated. On the one hand, admiration for Einstein's point of view. On the other hand, still holding on to his own views. And you see that in other cases as well. We also will see it, we won't see it, but it can be seen in the correspondence here with Max Planck and others on quantum theory, where he still, and with Einstein also on quantum theory, where he is really skeptical about some things, but still has deep admiration for Einstein's work, in this case on the light quantum. And that brings me to another point where you can see that he follows new developments very closely. We'll see that later on in his correspondence with discussion with Schrödinger. But he remained a classical physicist at core, at heart. He never could really reconcile himself with the idea to abandon classical notions of determinism and everything that's connected to the quantum ideas. He could not somehow, that was a step that was just too big for him, a conceptual step that he could no longer take, and that is something one can understand. I mean, if one has been working in classical physics for so many decades, for almost one's whole life, and has been very successful in that, and then suddenly one has to change the whole perspective on physics by adapting and incorporating quantum ideas, and then at a fairly advanced age. I mean, he was in his late 60s, early 70s. And it's very, very hard, and it's very understandable that he would somehow be unable to absorb those new developments. Now, this is, I already promised you that I will now move on to the more technical part, but still what I will do is give you a sort of a very, very brief pedestrian summary of quantum theory, highlighting some points that will occur later on in the discussion and that maybe sort of refresh your memory or maybe teach you a few things that you didn't know. Well, of course, we all know quantum theory started in 1900. That's the standard story, of course. Max Planck's quantum hypothesis, quantization of energy. Of course, it's a little more complicated than just saying that Planck quantized energy, quantized the energy of resonators in equilibrium with the electromagnetic field, with radiation. But anyway, that was the first quantization, the first step towards from a purely continuous worldview to a more discrete worldview was taken by Max Planck in 1900, and he used that hypothesis to derive a radiation law that tells you how much energy per in a certain frequency interval is contained in radiation, black body radiation. And of course, Planck's radiation law came just in time to explain all kinds of experimental discrepancies that people were finding between the existing radiation laws, Rayleigh-Jean's law, Wien's law, and the experimental facts. And that became a major point of discussion. How can this Planck radiation law is clearly something that's experimentally valid, but the derivation needs a hypothesis that we really cannot understand on classical grounds. How can we reconcile that? And that started the whole discussion of quantum theory, the whole development of quantum theory. Another milestone in this development is Albert Einstein's 1905 light quantum hypothesis, where Einstein makes the hypothesis that light sometimes behaves as if it consists of localized packages of energy, localized light quanta, and of course he could give an explanation of several phenomena, including the electromagnetic effect, or the photoelectric effect by this hypothesis. But Einstein's light quantum hypothesis remained controversial really until the late 1910s, early 1920s. It was only Millikan's experiments on the photoelectric effect, and later on, of course, the Compton effect that made people really aware of, or maybe convinced them of the existence of light quanta. And for a long time, Albert Einstein himself was the only one who really believed in the existence of light quanta. And then, of course, another milestone, 1930, Niels Bohr uses the quantum hypothesis to, his hypothesis that energy levels in atoms, and specifically in this case in the hydrogen atom, are quantized, and transitions from one quantized state to another one, in a transition, light is emitted or absorbed according to the quantum rule that the energy equals the Planck's constant times the frequency. And that gave a perfect explanation of the spectral lines, the spectrum of hydrogen, as it had been observed, including the so-called Rydberg constant, which you could calculate to great accuracy. And again, this was something that you had a result that, like Max Planck's radiation law, a result that fitted very well with experiment, but people couldn't really understand what was really going on from a physical point of view. How can we explain the stationary orbits in a hydrogen atom, and how could we explain that those electrons are on those stationary orbits without actually radiating energy, whereas they are accelerated, and according to classical theory, accelerated charges will radiate energy and will just lose their energy in radiation. So this was all very difficult to understand, and there was a lot of discussion on that, and there was a lot of stuff going on that people couldn't really make sense of. So those three things, I mentioned them because they will come back in my discussion. Now let's just give a short insight in Lorentz's ideas about quantum theory. I already mentioned that he was the quintessential classical physicist, though he had a lot of problems with the whole idea of quantization. But in one thing that he did in 1908, without really wanting to do, because this is sort of an unwanted result that he reached, what he was trying to do is to give a derivation of a radiation law starting from purely classical grounds, using the most general classical system that he could think of, a system consisting of in a rectangular box consisting of radiation, neutral particles, and charged particles. And he succeeded in using the then still fairly recent techniques of Gibbsian statistical mechanics I mean, that was also, by the way, if you look at that paper that he published in 1908, it's really impressive how he actually applies Gibbsian statistical mechanics to that system of radiation and particles. And then he shows that the only radiation law that one can derive from within the framework of classical theory, starting from such the most general mechanical system that one can think of, the only radiation law that one can derive from that is the Rayleigh-Jeans law, and not the Planck law. And of course, and then the mistake that I was just referring to, that Lorentz makes, is that he concludes from his calculation that the Rayleigh-Jeans law must be the real and only radiation law, and that the discrepancies between the Rayleigh-Jeans law and the Planck law must be due to experimental problems. Maybe, for instance, the experimental setup that one uses is not quite in equilibrium, and one needs to wait a long time for radiation to be in equilibrium with the resonators or with the ether, if you want. And this, of course, he was quickly disabused of by Wilhelm Wien, who actually told him that if the Rayleigh-Jeans law is valid, then a simple bar of silver should be visible in the dark at room temperature. Well, this is a clearly experimental fact that everyone can verify or falsify, and we all know that a bar of silver or even a little piece of silver will not be visible in the dark at room temperature. But that's something that would be an inescapable conclusion of the validity of the Rayleigh-Jeans law. But what he had done, I mean, if you look at it from a more general or higher standpoint, then you can say that what Lorentz had shown, that there is really a discrepancy between classical theory and quantum theory, and that you really need something additional, something extra, to find, for instance, Planck's law, or to other quantum phenomena, that classical theory just clearly is not enough. You need something more, you need something extra. And so classical theory needs to be amended by whatever it is, quantum hypothesis or something else. But at the same time, he remained skeptical about the quantum theory, and one of the things why he was skeptical is that we come to the light quantum that I just mentioned. He couldn't understand, and neither could a lot of other people, how can we explain phenomena like interference, by assuming that light quanta are localized. How can we those typical wave-like phenomena that we can easily explain by assuming that light is a wave phenomenon? How could we explain that by assuming that light consists of particles? Also, if you look at experimental facts, then we can also derive or guess or estimate that those light quanta really need to be very large, and that localization, I mean, they need to be very thousands of wavelengths large, much larger than would follow from the real from the light quantum hypothesis. Well, there was all kinds of problems that he saw. Of course, again, what we see here is that what you try to do is to try to explain a purely quantum phenomena by using in the language of classical physics. And of course, the whole idea of the wave-particle duality that we now all very familiar with was never something that occurred to people in those days. I mean, we're talking about the years around 1910. So his skepticism, he shared his skepticism with many people, and I mean, it's only, I just mentioned the Millikan experiments on the photoelectric effect. One of the reasons why Millikan started working on the photoelectric effect around 1914, 1915, that he had decided that he wanted to get rid of that stupid idea of light quanta once and for all. And the reason and the way to do that was to do experiments on the photoelectric effect and disprove this whole the connection between light quanta and the photoelectric effect, or the explanation that light quanta gave of the photoelectric effect. And then, of course, Millikan had to grudgingly admit after a few years that the only way to explain what was going on in his experimental results was the assumption of the existence of a light quantum. And of course, that's effect is the best way for an experimental physicist to find a positive result, by starting out with a bias towards the other possibility. He started out with a bias towards light quanta don't exist, but his experimental evidence was so strong that he had to conclude that light quanta do exist. And here's a nice quotation from 1923, and maybe in a way it's a quotation that we could still sort of understand. And he says all this, and he's talking about quantum theory. This is a lecture he gave in 1923 at the Société Française de Physique in Paris, and he says it's of great beauty and importance, but we do not understand it. And maybe we still don't understand it, or at least we don't understand a lot of it if we just try to understand it in classical terms. And then he says, and then he makes sort of a prophetic pronouncements. He says, to be honest, the mechanics of quanta, the mechanics of discontinuities still has to be made. And that, it's 1923, so he's sort of predicting what was going to happen. Mechanics of quanta, or what we now call quantum mechanics. So, let's talk a little bit about Schrödinger. Of course, you all know more about Schrödinger than I do. But let's just quickly summarize the main data of his life. Born in 1887, died in 61. Of course, he was born in Vienna. In 21, he became professor in Zurich. Then he became successor to Max Planck in Berlin. 33, he won the Nobel Prize for his work on wave mechanics. Then, of course, he had to move to Dublin because of the political situation in Austria, and he stayed in Dublin until his retirement there. And in '56 he returned to Vienna to spend the last 5 years of his life in Vienna. So he remained a real Viennese, I would say. But what we're going to talk about now is that he's in the first years of his career. He did a lot of interesting things, but nothing really revolutionary. Mainly stuff in classical physics. But in 26, he suddenly developed his what we now know as his wave, or what he already then called his wave mechanics, and that, of course, made him world famous and earned him the Nobel Prize. Now let's talk a little bit about what Schrödinger, what inspired Schrödinger to this whole to the development of his wave mechanics, because that's something that is not very widely known nowadays. And it's something that when I was first confronted with it, I thought it was very beautiful and very interesting. And he was inspired by two things. And the first thing is optics. Now, if we talk about optics, we can talk about wave optics. Wave optics, the light is represented by waves, by a series of waves. And we have a wave equation that tells you how the wave develops in time. And we also have geometrical optics, or ray optics, where we look at light rays that go straight or get diffracted in prisms or what have you. And then, so we have two kinds of optics: the full wave optics and the geometrical optics. And the geometrical optics is an approximation of the wave optics. It is an approximation that we can use if the wavelength of the light is small. So there's in the medium in which the light propagates, the properties of the medium don't change much over one wavelength of the light that you're in, and then you can use geometrical optics, which in a lot of cases is a lot easier to work with than wave optics. That's the first part, and the second part is mechanics. And in mechanics, it was known, and it was something that was also being taught at university courses, in classical mechanics courses. Hamilton had shown that there is a very deep, a very interesting, very beautiful formal analogy between mechanics on the one hand and geometrical optics on the other hand. And the analogy is that you can have, you have essentially the same mathematical formalism that you can use for both. And it's very surprising that something as those two fields, things as different as mechanics and optics, geometrical optics, can be described with the same mathematical formalism. I'm not going to go into any details, but you have to believe me that this is a very deep and interesting analogy, and that the formalism is really, you can translate one formalism to the other one to one. And that, of course, I'll give you a little, do it a little schematically and more suggestively what this suggests and what this suggested to Schrödinger. We have wave optics, and then we have the limit of wave optics, and you get geometrical optics. Now we have the analogy between geometrical optics and mechanics. You see here the double arrow here. Now, this already is quite suggestive the way I've written it down, because we have an empty spot here. And let's add the arrows here. So would there be something that in the limit becomes mechanics, and that has a formal analogy with wave optics? Would there be something like what we might call wave mechanics? So would there be a field or a formalism that we can, that in the limiting case would become mechanics, and that uses the same formalism as wave optics does? So a wave theory of mechanics. Now, of course, and this was Schrödinger's question: can classical mechanics be generalized to a more general wave mechanics? Of course, when Hamilton developed the analogy between geometrical optics and mechanics, there was no reason whatsoever for him to suppose that mechanics might also have a generalization that would have a sort of a wave-like character. So Hamilton never followed up on, he never felt that this needed to be filled in, this hole, this empty spot. But Schrödinger felt that maybe it would be a good idea, because maybe the generalization that you would have here, from here to here, would be able to explain all kinds of quantum phenomena. Maybe that would be a candidate for the mechanics of quanta that Lorentz was already calling for in 1923. So what we have now, if you look at the Lorentz of Schrödinger's wave mechanics, which was really developed, especially in his second paper on Zeitenmitteilung on wave mechanics. He really does exactly what I was just sketching to you. He creates the generalization, and of course a generalization always is in a way arbitrary, because the only thing you know is that in the limiting case it has to be mechanics, but of course there are many possibilities to generalize things. But he developed something that was a wave mechanics, a theory in which there's a wave equation, a complex wave equation, which we now know is the Schrödinger equation, for a wave function, which is traditionally called psi, and he found also, that's already in his first paper, that this wave equation could actually account for typical quantum effects, such as the quantization of energy levels in the hydrogen atom. And the only problem is that optical waves are waves in three-dimensional space. Space as we know it, that we live in. Unfortunately, this wave function lives in a higher dimensional space. So it's very difficult to give a physical interpretation to it, or interpretation that we can sort of visualize for ourselves. Also, it is a complex quantity. It's not a real function, but a complex function, which also makes it a little more complicated. But still, this is the fact that he found this result is very important, and it's very promising. It's like Bohr coming up with his quantization ideas and getting the right result for the hydrogen spectrum without really knowing what he was doing from a physical point of view. So wave mechanics became a major candidate for the desired new mechanics of quanta. And of course, there was another candidate, which was the so-called matrix mechanics, developed in 25-26 by Heisenberg, in the first place by Heisenberg, and later by Heisenberg, Born and Jordan in the famous dry matter papers. And this, of course, this theory is very abstract and mathematically very challenging and very difficult to really understand what's physically going on. So, in a sense, those two candidates for the mechanics of quanta appeared almost at the same time. Now, just a little historical postscript. Schrödinger showed, in fact, this was sometime later, that those two mechanics, again, basic mechanics and wave mechanics, are mathematically equivalent. And again, there is a one-to-one correspondence between matrix mechanics and wave mechanics. So they are essentially not totally different theories, but they are the same theory, but in a different representation, one might say. Now let's talk about how Lorentz and Schrödinger discussed this whole thing, and how they try to get a grip on it. And what's interesting is that Schrödinger in 30 March 26, he sends Lorentz the proofs of his first two papers on wave mechanics. Why did he send them to Lorentz? It's not quite clear, but he must have felt that the one person in the world who would be able to say something about this whole new formalism, and also who would know about this beautiful analogy and the possible generalization of mechanics into wave mechanics would be the classical physicist, the ultimate classical physicist that Lorentz was. And Lorentz didn't disappoint him. He's already 72 years old, mind you. He replies with a 9-page letter. That was for a pretty long handwritten letter, and he's very much impressed. He clearly has studied those two papers really in much detail, but he's skeptical. And one of the things that he says is, of course, the wave mechanics has a greater Anschaulichkeit, greater visualizability, one might say. It's easier to think in terms of waves than in terms of matrices. I mean, most physicists didn't even know what a matrix was. Even Heisenberg didn't know what a matrix was when he developed he developed his matrix mechanics. He didn't know that he was dealing with matrices. It was Max Born, who had a very solid background in mathematics and had taken a course on matrices at Göttingen University, who actually pointed out to Heisenberg, "Hey guy, what you're doing here is you're working with matrices." And so Heisenberg, what's a matrix? So he had to learn what a matrix was. By the way, Lorentz also had to learn what a matrix was, and he learned very quickly. There is some discussion in Correspondence between Lorentz and Ehrenfest, in which Lorentz says some really pertinent things about matrices. You know exactly what he was talking about. For a 72-year-old guy, I mean, I think it's pretty impressive. Anyway, he says that greater Anschaulichkeit, that's a good point. But then, of course, how should we look at waves not in the usual three-dimensional space that we live in, but in a higher dimensional configuration space? How could we deal with that? I mean, what's the physical meaning of that? I mean, waves is waves, and it's interesting. It's nicer than matrices, but still. What do we do? How to talk about those waves? But of course, we are rid of those abstract matrices with a problematic interpretation. We don't have to worry about those things anymore. We can just now focus on the wave mechanics. And then, of course, one of his major, and that's his, one of his point that we come back again and again, is that he says, well, how we deal with particles. In classical physics, we have what we call a wave packet. And here's a wave packet. Oops, excuse me. Here's a wave packet. You see, that's it's a wave, but it's not a wave that goes on, but a wave that starts small and then becomes big, and that's the idea was maybe we can sort of construct particles from such kinds of waves, what we call a wave packet, a localized wave, localized in space and time, and maybe we can do that in classical optics. Maybe we can do that in wave mechanics as well. And Lorentz was, very rapid to point out that it didn't work in wave mechanics. So the kind of waves that you can construct with the waves that the wave function that obeys the Schrödinger equation, that they will spread pretty rapidly, and and the dimensions of that wave packet would be of the same order of magnitude as the atom itself. If you look at waves as electrons in a hydrogen atom, so localization is, is a difficult problem here. And he saw that as one of the major problems in Schrödinger's wave mechanics. And that, of course, led Lorentz to have doubts about, again, I've given you the schematics, about this wonderful little diagram here. And as he puts it, he says, Ihre Vermutung, dass die Umwandlung, welche unsere Dynamik wird erfahren müssen, dem Übergang von Strahlenoptik zu Wellenoptik ähnlich sein wird, klingt sehr verlockend, aber ich habe doch Bedenken dagegen. So he says he really likes the idea a lot, but he cannot he cannot somehow overcome the problems that he has found with it, and he really hopes that maybe Schrödinger will be able to counter those problems. Now Schrödinger was, of course, extremely pleased. He writes this 12-page, densely typed letter in which he starts with lots of thanks about. He talks about die außerordentliche Ehre, auf 11 eng beschriebene Seiten die Gedanken gegen meine letzten Arbeit in einer tiefgreifenden Analyse und Kritik zu unterziehen. Ich finde keine Worte, um Ihnen für dieses wertvolle Geschenk, das Sie mir damit gemacht haben, ausreichend zu danken. Es bedrückt mich schwer, dass ich Ihre Zeit damit so ungebührlich stark in Anspruch genommen habe. I think Lorentz really, he didn't feel that Schrödinger was imposing on his time. I think Lorentz really liked what he was doing. He liked to get his teeth into this little problem, or big problem here. Anyway, then he tries to refute Lorentz's objections. He thought, for instance, the wave function, he says, well, you should look at the wave function itself, but it is the absolute value psi times the complex conjugate, and then you have at least you have a real number. And he says this thing we can connect with the charge density in physical space. But there was an early idea of Schrödinger's that this would be the physical interpretation of the absolute value of the wave function. And on the spreading problem, he says, well, he has done a calculation himself, and he has, for instance, looked at the quantized harmonic oscillator, and he says, well, for a harmonic oscillator, we can actually construct a wave packet that's stable. And the idea is that this would be, maybe the right road to pursue to find stable wave packets also in other cases. And then about the individuality of electrons, about the whole thing about how can we look at, can we distinguish individual particles, he says, he really takes a step back from the classical interpretation, saying, wir würden Sie für einen sehr schweren Einwand gegen die Theorie halten, wenn sich ergeben sollte, dass im gewöhnlichen Sinn freie Elektronen ihre Individualität nicht dauernd bewahren. That's a major conceptual step that he now takes, that there's no such thing as individual electrons, at least free electrons, dass das Sprechen von einzelnen Elektronen im Kathodenstrahlbündel vielleicht nur den Sinn hat, das Bündel besitzt eine gewisse körnige Struktur. And again, this is, it's trying to find a way out of the problems, trying to develop new ideas, develop new views of of how one should look at particles, how one should look at atomic systems, and taking a step back from the old classical ideas. Lorentz's reply is even longer than his first letter. It's dated 19 June, very rapidly after his Schrödinger's reply. It's 18 pages, and those are not just regular pages, but they are about this size. And they are, as you see, they're densely written with calculations. He starts out with calculations and goes on throughout those 18 pages. I mean, it's really amazing how the mastery of this whole wave this wave physics that he shows is pretty amazing. And in his letter he says again he raises the problem: how can we construct wave packets that move like bound electrons, for instance, in the hydrogen atom? And he doesn't see how one can do that. And then he says, well, he tried something, and he's doing a very lengthy, very complicated calculation, and he says, well, let's assume that one can construct such stable particles. I don't know how to do it, but how can we construct them? And then he tries to calculate how will they move. And he says, well, and then he does lengthy calculations, and his conclusion is they don't move, they don't behave like bound electrons. And for him, that's, again, is a major problem. And then again, he comes back to the whole idea, the inspiration, Schrödinger's inspiration. And he says, wenn wir die Wellenpakete aufgeben müssen, und damit einen der Grundgedanken ihrer Theorie, die Umwandlung der klassischen Mechanik in eine undulatorische, so würde damit etwas verloren gehen, das sehr schön gewesen wäre. Es würde mich sehr freuen, wenn Sie hier einen Ausweg finden könnten. No, that didn't work. He couldn't find an Ausweg. Schrödinger couldn't find an Ausweg. Lorentz couldn't find an Ausweg. So that's where it's sort of the beauty of the analogy ended here, so to speak. On the other hand, the inspiration had brought Schrödinger to develop the wave mechanics. So the analogy may have been flawed, but it was at least pretty productive, one might say. In the following years, Lorentz continued to work on wave packets. He didn't abandon the idea, but he never got anywhere with the kind of localization that he was looking at. Well, finally, to sort of a conclusion, what can we see in those letters? Well, we see that he shows a 73-year-old Lorentz shows an impassive mastery of classical physics, and his criticism really impressed Schrödinger, and Schrödinger was really taking it very, very seriously. And I think one of the things that Lorentz's criticism did was make Schrödinger aware of the essential non-classical character of Schrödinger's wave mechanics. And as we have seen, eventually, the whole idea about the transformation of classical mechanics into wave mechanics, in the sense that I showed you, the analogy, etc., was abandoned by Schrödinger. But it's like the famous metaphor that Wittgenstein uses, that once you have climbed the ladder to reach the level that you want to go to, you can throw the ladder away. And in a sense, Schrödinger had developed his wave mechanics, and he didn't need the analogy any longer to get there, but he needed the analogy to get there. That was his ladder. Once he got there, well, he didn't need a ladder. This 73-year-old classical physicist, contributed in a sort of essential conceptual way to develop the wave mechanics. Thank you.